Most people look at a building and just see the concrete. But if you're in this industry, you know the truth. The concrete is just the receipt. The actual engineering happens weeks before inside a mold. We see a lot of projects fail not because of the mix design and not because the reinforcement was wrong, but because the mold strategy didn't match the production reality. So today we are going to go deep and understand this. I'm going to walk you through the material selection framework we use at Modular Pulse, and we're going to look at the physics of steel versus wood or timber versus composites. I'm going to show you exactly how to choose the right tool for the job. So let's get into it. First, we have to change how we define a mold. It is not just a bucket that holds wet mud or concrete. It is a precision instrument that has to manage three specific forces: hydrostatic pressure, thermal energy, and vibration. Look at the diagram. Vibration transmissions is the silent killer for quality. If your mold material is too soft or damp, it absorbs the energy from your vibrators. That energy should be going into the concrete to remove air pockets. If the mold steals that energy, you get honeycombing. On the flip side, if the mold is too rigid but lacks mass, it can resonate at a frequency that separates your aggregate. So, before we talk about materials, remember, stiffness and mass are not just about durability, they are about consolidation. So when do we use steel? This is the heavy artillery. We use steel when we need to do three things: mass, conductivity, and cycle life. Steel has a high thermal conductivity. This is crucial if you are steam curing. A steel mold acts as a heat exchanger, transferring that energy directly into the concrete core to accelerate hydration. If you tried with wood, the wood acts as an insulator, and your cycle times double. We actually saw this recently with a client working on a massive highway infrastructure project, Jersey barriers, thousands of them. They started with composite mold to save money upfront. The problem, the molds couldn't transfer the steam heat fast enough. They were stuck at a 48-hour turnover. We came in and transitioned the line into high gauge steel. Because of that thermal transfer, they could hit the target temperature faster and strip the molds every 24 hours. They literally doubled their daily output by just changing the mold material. That is the power of matching the material to the method. Now let's talk about the opposite end of the spectrum: timber or wood. Wood is fantastic, but it is misunderstood. It is material of agility. You choose wood when the design is still fluid. If you need to move a chamfer strip or change a blockout size, you can do it in 5 minutes with a screw gun. You can't do that with steel. However, wood is hygroscopic. It drinks water. Every time you cast, the wood swells slightly. Over 50 casts, your dimensions will drift. So the strategy here is use wood for prototypes, one-offs, or short runs where tolerance drift is acceptable, but never for mass production. What happens when you need the durability of steel but the complexity of a sculpture? That's where fiberglass GFRP comes in. Steel hates curves. Bending steel plate is expensive and inaccurate. Fiberglass loves curves. We can create seamless, double curved surfaces that are completely watertight. Also, consider the environment. GFRP is inert. It doesn't rust. If you are casting white concrete or using aggressive chemical admixtures that might react with steel, fiberglass is the safety zone. It yields a Class A surface finish right out of the mold, often eliminating the need for sacking or patching later. Sometimes the challenge isn't shape, it's the texture. If you want a wood grain finish or a chiseled stone look, you cannot mill that into the hard mold. You would never be able to demold it. The concrete would lock into the grooves. This is where elastometric liners, rubber or polyurethane liners, saves the day. They are flexible, and when you pull out the panel, the rubber stretches and snaps back, releasing the concrete from the deep undercuts without breaking the edges. We had an architectural project where the architect wanted a facade that looked like natural craggy limestone. The challenge was that the cracks were so deep, a rigid mold would have ripped the face off the panel during stripping. We sourced a specific high-shore polyurethane liner for them. It was tough enough to hold the weight of the wet concrete, but flexible enough to peel away during demolding. They got the aesthetic of the stone with production speed of a factory line. Let's look at the future. Additive manufacturing. Traditionally, if you wanted a complex shape, you had to carve a plug out of a foams and seal it, and then build a fiberglass mold over it. It's slow and it's wasteful. With large format 3D printing, you can print the mold directly. You use thermoplastic composites that can be machined down to a mirror finish. And the best part, it's circular. When the project is done, you can shred the mold, melt the plastic, and print the next job. This is decoupling complexity from the cost. This is one of my personal favorites, fabric formwork. Concrete is a liquid. It wants to flow. When we force it into a square box, we are fighting physics. Fabric formwork uses geotextiles to hold the wet concrete. Under the weight of the mix, the fabric bulges into a natural funicular curve. This puts the concrete exactly where the structural forces serve it best. You end up with columns and beams that are 40% lighter and just as strong, simply because you let gravity do the design work. I want you to screenshot this slide. That is the trade-off matrix. Notice the relationship between capex, which is initial cost, and lifespan. Steel hurts your wallet on day 1, but is costing peanuts on day 1000. Wood is cheap on day 1, but if you try and use it for day 100, you will be rebuilding it, and your labor costs will skyrocket. GFRP sits in the middle. It's a balance point between geometric freedom and durability. Now, none of this matters if you don't treat the mold as an asset. The number one reason we see molds fail early is chemical incompatibility. You cannot grab any drum of release agent. Some water-based agents will cause flash rust on your steel if you aren't careful. We walked into a plant recently that was complaining about their polyurethane liners warping after 20 casts. They thought the liner was defective. We checked the release agent. It was a petroleum-based product that was chemically attacking the rubber, making it swell. We simply switched them into a vegetable-based barrier-style release agent. The swelling stopped immediately, and those same liners are now running past 200 casts. That one chemical tweak saved them about 6 lakhs in replacement tooling. So how do you decide? Use this framework. Start with volume. Are you making more than 1000 units? If yes, stop thinking and buy steel. If no, ask about geometry. Is it flat? Use wood or steel. Is it curved? Use GFRP or 3D printing. Is it highly textured? Use Elastomer. Don't overcomplicate it. Follow the volume, then the shape. There is a saying we use here. The quality of your product can never exceed the quality of your mold. If you are fighting your concrete, stop and look at what you're pouring into. The right strategy doesn't just improve the finish, it improves your cycle time, your structural integrity, and ultimately your bottom line. This is the kind of thinking we apply to every line we design. If you want to nerd out more on precast engineering, subscribe to this channel because this is what we do here. I'll see you in the next video.